Can people hear me? It's a bit loud. Okay. Okay, let's see how this will work out. Thanks for inviting me. It's a pleasure to be here. I've never been to this town, but I've been to China many times. It's always good to be here. I'm going to talk about in-memory computation. I'm a bit uncomfortable with this noise, but I'll try to. If it becomes too loud, please let me know. And we'll hopefully cover a lot of interesting topics in the meantime. Okay, let's get started. Okay, this is starting from the back. Usually you shouldn't start a presentation from the back to the beginning, right? Although that could work in some cases too. Okay, let's do it right. Start from the front. Okay, so I will talk about main memory. If you look at a system today, it consists of processors, caches. Okay, that doesn't work also. Let me do it this way. Okay, apparently I need to point to my computer. Okay, that's better. And main memory is a component. Turned off the mic. That's better. Main memory is essentially a critical component of all computing systems that we design today. Whatever kind of computing system you're designing, you need to have some sort of working storage. And main memory essentially sits in between processors and storage. And this system must scale in many, many dimensions in terms of its size, technology, efficiency, costs, and the algorithms we use to manage it if we want to maintain the performance growth and technology scaling benefits that we've been used to for a long time. And it doesn't matter what you attach to main memory, what computation you attach. Processors, FPGAs, GPUs, a heterogeneous combination of these different types of accelerators, you're bottlenecked by main memory. This is another picture of the main memory system. This is my cartoonish picture drawn in Xfig a long time ago. And if you look at this picture, there are two observations. One is most of the system that we design is dedicated to the main memory system. Cores are only a very small part of the system. Only these red parts are dedicated to core. Everything else is dedicated to the memory system. And if you do the calculations, more than 90% of a single system, single node system is dedicated to memory. And the second observation is that main memory is shared across these different cores. We're not going to talk about the sharing aspects of main memory, but it's very fundamental. Okay, so let me tell you in one slide the state of the main memory system as I see it today. There are some recent technology, architecture, and application trends that lead to some new requirements from the system and that exacerbate some old requirements. And we've always demanded a lot from the system. We're going to demand a lot more. And I will show you, hopefully, that DRAM, the main technology that we design memory with, and memory controllers, as we know them and as we design them today, are unlikely to satisfy the requirements that we're putting on memory. And there are some emerging memory technologies that happen to be non-volatile that enable some new opportunities, like the merging of memory and storage, or in-memory computation in place. Given these trends, I believe we need to rethink the entire main memory system and the systems we're designing around it. In fact, we're designing most of the systems as memory today. As I showed you earlier, 90% of the system, more than 90% is dedicated to memory. So we really need to rethink the systems we're designing to fix the issues we're having with memory and enable some of these emerging technologies, while of course satisfying all of these requirements. So let me tell you a little bit about the trends that are affecting main memory. What are the things that are bothering us today? And this is again in one slide, three major things. Basically, the first bullet over here is about performance. We want more capacity, more bandwidth, more quality of service, predictability, better latency, better performance overall. And this is really driven by three major trends. The first trend is computation is not a problem. We can put many, many accelerators on a chip. So we're very good at that. So we can do that very efficiently. And that's driving the bandwidth, capacity, and quality of service requirements up. Applications are becoming increasingly data intensive, and it's not going to stop anytime soon. And we want to consolidate more and more. We want to put many applications on a single node so that we can get more efficiency. And all of these together is increasing the capacity, bandwidth, and quality of service requirements up. I'll give you some examples of this. This is one example. It's old data from HP Labs at University of Michigan, where they showed in this paper that DRAM capacity is not increasing as fast as core count. Now, you could argue with all of these numbers, and as good students, it's always good to argue with the numbers. But if you plot these trends in GPUs are actually following this trend. GPUs are very much capacity bottleneck. That's true also for high-performance systems when you take into account accelerators that we're putting into the system also. Essentially, memory capacity is expected to drop per core is expected to drop by 30% every 2 years, which is not good news for software because software relies on having more memory capacity for better features and better performance over time. And if you actually plot the trends for memory bandwidth per core, they're much worse. Essentially, we're able to put a lot of computation on a chip, but we're starving these computational units today in terms of both capacity and bandwidth. Now let's have some fun with numbers in terms of DRAM chips. In the last 18 years, let's take a look at what happened to the DRAM industry in terms of capacity, bandwidth, and latency. If you plot the common technology of the day, DDR technology of the day, from 1999 to 2017, how much do you think the DRAM capacity has improved over the 18 years? Any guesses? 10, 100? Nobody bold? Yes? Maybe 100. Well, if you guessed 100, you're close. It's actually 128x, which is really what DRAM chips are designed for. Capacity is what DRAM chips are designed for today. So if I do this correctly, this should work, but it's not working. That's okay. And if you actually, essentially, but you can see that we're actually having trouble right now. Capacity is not improving as fast. Okay, what about bandwidth? Bandwidth has improved significantly also, about 20x in the last 18 years. If you look at latency, latency is suffering. Essentially, latency has not improved as much in the last 18 years or so. And basically, we have a big problem with latency, memory latency. It's because we're not designing these chips to be low latency. And they can be designed to be low latency. I'm not going to talk about the research related to that today, but I'm going to talk about related research that can reduce the latency in a different way by pushing computation towards the data. But these trends are very telling, I think. Even though we're designing the DRAM chips for memory capacity, we're not doing well in memory capacity because of DRAM scaling issues in recent years. So even the main design criteria we are failing at today. But of course, we know that memory is critical for performance. There are many applications that are performance bottlenecked because of memory. And I'm going to talk about these applications hopefully later. These are on the lower end, although they're not lower end necessarily. These systems are some of the highest performance systems that we have today, given the energy budget. Okay, so let's talk about the other trend. The other trend is energy and power is a key system design concern today, and memory is consuming a lot of it, most of it actually. So if you go back to 2003, data from IBM research in this beautiful paper written by Charles Lafergie et al. Suggests that 40 to 50% of the entire system energy is spent on the off-chip memory hierarchy. Fast forward about 10 years, IBM writes another paper talking about the power consumption in IBM Power 8, and they say more than 40% of the entire system power is just in DRAM. So over the course of 10 years, a lot of stuff got integrated on chip. As a result, they became power efficient, but memory stayed off chip. As a result, it is consuming a lot of power today. That's true for GPUs also. There are a bunch of results that corroborate this number over here. One of the issues with DRAM is DRAM consumes power because you need to periodically refresh it, and that's becoming a big issue in terms of scaling DRAM also. I'm not going to talk about that as much, but keep that in mind. Going forward, refresh is going to be a bigger problem than today. So on top of all of this, DRAM technology scaling is ending, but I will talk about that in a little bit. It's really tied to refresh especially. So one example of the energy waste that we have in systems today, this is a paper that we wrote with Google a couple of years ago, it's in 2018 actually already. We showed that more than 60% of the entire system energy is spent on data movement in these workloads that are really interesting. And we're going to get back to this. We're going to try to solve the problem by pushing processing closer to memory in these workloads on mobile devices. Okay, so on top of all of this, DRAM technology scaling is ending. For a long time, International Technology Roadmap of Semiconductors has been projecting that the future size of a DRAM cell will not easily scale below some number of nanometers. And I put X over here because I don't want to change my slide while they change their numbers. But we're going to talk about X later on. Basically, by reducing the size of a DRAM cell, we can actually increase capacity, have lower cost, have reasonable energy scaling. That's great. But it's becoming more difficult to reduce the size of a DRAM cell for reasons we're going to talk about, because it's becoming less reliable to do so. And as a result, if you're not able to scale the DRAM cell below some number of value, then it's going to be difficult to satisfy all of these other requirements up there. So scaling is very fundamental because of that reason. If we're not able to scale memory, we're not going to be able to satisfy the requirements, which keep increasing on us over time. Okay, let me talk about scaling a little bit more, and then I'm going to motivate processing in memory from this direction first. DRAM scaling is already becoming difficult. There are many issues that are documented. It's difficult to significantly improve capacity and energy. As a result, emerging memory technologies have appeared and they're very promising. Even DRAM is becoming proliferating in the sense that it has different types of DRAM. So we have 3D stacked DRAM, it has some benefits. We have reduced latency DRAM, it has some benefits. We have lower power DRAM, it has some benefits. And then we have emerging memory technologies that are clubbed into this little corner over here, but there are many of them clearly. And they have some benefits. But of course, there is no single memory technology that's good at everything, so you see the most salient negatives of each technology over here. As a result, we have this picture in the memory system design space today that no memory technology is green at every metric that we want. So as a result, people actually move into heterogeneity in the memory system. So we have hybrid memories going forward. This is one example of it. You have some technology, you basically combine together different technologies that are green at different things and that are red at different things. And you design the hardware and the software to manage the data allocation and movement to achieve the greens as much as possible while avoiding the reds as much as possible. This is already happening, it's going to happen even more, and it's going to happen in different metrics also. Again, I'm not going to talk about this in detail, but I will give one conclusion over here. If you look at the system, if you really want to manage the system really well, you really need to have an intelligent controller over here. So that's my first foreshadowing of the need for intelligent controllers. If you have a hybrid memory system, you really need to have intelligence in your controller so that you can manage the data. And there's a lot of aspects of that management which we're not going to go into in this particular talk. That would be a talk by itself, actually. Okay, so the scaling issues are actually real. I'm going to give you evidence from the field, but I will talk about this paper very briefly. This is written by two companies that normally don't talk to each other, Intel and Samsung. And they actually wrote this paper, beautiful 4-page paper together in 2014, where they said that they're having difficulties with DRAM technology scaling for reasons that are shown in the slide. I'm not going to go into in detail. But basically, they propose the same solution that we've been advocating for a long time. Basically, it's a good idea to make the controllers more intelligent so that they can cover up for some of the issues that we're seeing at the technology level. And this will become more concrete as I talk about the Rohammer problem in a little bit. Okay. So this is the agenda that I have for the talk. It's an aggressive agenda. I have a lot of slides. So the best way to understand this talk is actually not try to read the slides, but listen to me, probably, and I'll just guide you through the slides. Basically, we will talk about motivate intelligent memory controllers from two dimensions. One is bottom up. There's a huge push from circuits and devices that are asking us to have intelligent controllers. And I'm going to motivate it top down also. Applications and systems are demanding intelligent memory controllers today. So we're kind of squeezed in the middle. We really need to do something different with our memory controllers so that they can do computation. They can be more intelligent. And then I'm going to talk about processing in memory and talk about two different aspects as much as possible, as much as time permits. And then we're going to talk about adoption issues, and then we're going to conclude. Does that sound like a good plan? Okay, perfect. So before I start, I'm going to start with psychology. This is actually an American psychologist who had a lot of influence in a lot of things, psychology, economics, politics. And he's probably more famous for what is over here. This is the hierarchy of needs, and this is Abraham Maslow. He dedicated his life to understanding why people do the things they do. And I'll use this as a fabric to motivate some of the needs in memory also. So basically, Maslow, when he actually talked about human motivation, he said that for humans to be able to do many interesting things, they first need to have their safety and reliability needs satisfied. They need to be basically safe and secure. That's why I think that's true for computers also. And when I talk about computer security, this is actually the slide that I use to motivate freshmen when we go into computer security. I also use this slide, which is a bridge in Washington, which used to be a bridge in Washington. It's the Tacoma Narrows Bridge. It was built in 1940 and it collapsed 6 months later. Why did it collapse? Because there were Bitflips over here. Well, it was not Bitflips, it was Bitflips in a larger scale. Basically, there was aerostatic flutter. As a result, over time, the bridge collapsed. And you can read a lot of beautiful pictures and videos and stories about this as to why this collapsed. But from my perspective, we're building infrastructure today that is actually going to be used for many things as computing people. And if computers are vulnerable to such Bitflips, we're going to have a lot of these safety and reliability and security issues. To me, this is a perfect example of safety, security, reliability collapsing at the same time, because it could be any of those. I also give this example to the students in my class. Basically, these folks are very happy right now constructing Manhattan after World War, but if there's a Bitflip on the rod they're sitting, they won't be very happy soon. Right? Okay, so I believe security is about preventing unforeseen consequences, and in memory I think we're having a lot of problem with unforeseen consequences. I'll give you one example of this. Basically, I'll talk about the DRAM scaling problem because we have a lot of Bitflips in DRAM. So let's go into a little bit more detail. Probably most of you know this, but this is, any memory technology needs a storage device and an access device. And in DRAM, the storage device is the capacitor, the access device, the access transistor, the bit line, and the sense amplifier. For any memory to work, both of these components should work reliably. Now, as you reduce the size of a DRAM cell, both of these components become less reliable. Capacitor becomes smaller. As a result, reliable sensing becomes difficult. Access transistor becomes smaller. As a result, leakage increases. So as a result, refresh becomes a bigger problem. And this was the value that was assigned to X by ITRS in 2009. They said reducing the size of a DRAM cell below 35 nanometers is challenging. And they were absolutely correct. Okay, does anybody know what's the size of a DRAM cell today? In 2019, that's 10 years later. I didn't hear much, but basically today we're at 17 nanometers. Clearly we're below 35 nanometers. Well, they didn't say it's impossible, they said it's challenging. And they were absolutely right, actually. So basically, this is data that we collected with Facebook. This is data from all of Facebook's servers worldwide. There's a lot of servers, there's a lot of memory in there. They don't let us publish how many servers and how much memory because they're worried that it will affect their stock price. But maybe they should be worried about some privacy issues related to their stock price. Although they've been doing quite well, I think. Anyway, if you look over here, this plots across all of these servers the correlation between the chip density used in the server, DRAM chip density, and the error rate that you get in the server. And you see that there is a strong correlation. As chip density increases, server failure rate increases because you get more Bitflips. And this is one example of that DRAM is becoming less reliable as you put more cells, as you cram more cells into the circuit. And if you're interested, you can read this paper in more detail. So we've also built a lot of infrastructure at the low level to be able to understand these issues. This is our earliest infrastructure, FPGA-based infrastructure to test DRAM so that we can uncover some of these problems related to scaling. I'm going to talk about a couple of these, and this is our later infrastructure, and this is one of the infrastructures where we discovered the Rohammer problem that I'm going to talk about. We actually open source this infrastructure. People are using it. It's very easy to use. It has a C++ API to program the FPGA so that you can do memory experiments. We'd be happy to support it if people here are interested in using it also. So one of the things that you can study in DRAM is refresh when you actually have an infrastructure like this. And in this paper, we reported that today we are refreshing DRAM, every DRAM cell every 64 milliseconds. But you don't need to do that. If you actually look closely, if you understand the retention time profile of different DRAM cells, it's very heterogeneous. There are only a small number of cells that you need to refresh very frequently, and a vast majority of the cells don't need to be refreshed very frequently. If you can identify this, you can get rid of 75% of refreshes. As a result, you can have much more scalable DRAM. Of course, to be able to do that, there are a lot of challenges, which I'm not going to go into, because the refresh retention time of a DRAM cell depends on the location, depends on the stored value pattern, it depends on the time also. So there's actually random quantum-like effects that you need to overcome. So you actually need to have some ECC error correcting codes to be able to do that. I'd be happy to talk about this. But what is clear is if you want to take advantage of this phenomenon, you really need an intelligent memory controller that figures out what is the retention of a DRAM cell at this point in time. This is another example where you really need intelligent memory controllers. And this is exactly an example of what those folks from Intel and Samsung were talking about. If we're having a problem with DRAM refresh, we can actually solve this problem by having intelligent memory controllers that understand the retention time of different DRAM cells and refresh each cell at the rate it requires to be refreshed. If you're really interested, you can actually read these papers. These slides will be available. I'm not going to go through it. If we actually had to talk about refresh, that would be a talk by itself. It's actually very fun. Okay, so while we were actually doing these studies, we stumbled upon an error model in DRAM that really should not happen. And the error model is that you can predictably induce errors in most DRAM memory chips that you can buy in the field today. Now this is known as the Rohammer problem. It's essentially a simple hardware failure mechanism, a Bitflip that you can induce reliably that can create a widespread system security vulnerability. And people are writing papers that are, actually articles that are like this. This is from Wired magazine that says, forget software, hackers are exploiting physics. And this is a perfect explanation of Rohammer, I think, because it's really all about physics at the low level. So if you look at what's happening, any memory consists of rows. In this case, it's DRAM rows. If you actually want to read a cell in a DRAM row, you need to activate the row. Basically apply high voltage to that row. If you want to read some other cell in some other row, you need to deactivate this row, meaning pre-charge in DRAM. You basically apply low voltage. So if you keep doing this repeatedly, activate pre-charge, activate pre-charge, activate pre-charge, activate pre-charge, activate pre-charge, activate pre-charge, enough times before the cells get refreshed, it turns out in most DRAM memory chips, you'll get Bitflips in adjacent, physically adjacent rows. Now clearly this should not happen because you're just reading memory, right? You're not doing anything else. You're not even writing. Of course, read and write are symmetric in DRAM, so it doesn't matter. But you should not get Bitflips by doing this. So we call this the hammered row, we call this the victim row, and we show that more than 80% of the chips that we've tested from three major manufacturers are vulnerable to this problem. So it's an industry-wide problem. It's not specific to any manufacturer. It's a scaling problem because chips that were manufactured before 2010 did not have this problem. The first occurrence is in 2010, and all of the chips that were manufactured between 2012 and 2013 that we tested were vulnerable. And you can see that it's really all manufacturers, it doesn't matter. So at some point, DRAM cells became too close to each other that they start affecting each other. So why is this happening? Basically, there are multiple reasons for this, of course, but the most intuitive explanation is really electromagnetic coupling. Whenever you're activating a row, you're slightly activating the adjacent row also. And when you slightly activate the adjacent row, the vulnerable cells in that adjacent row leak little. If you keep doing this activation, you're leaking those vulnerable cells little by little. If you're not refreshing DRAM very frequently, you can actually leak some of these cells, some of these vulnerable cells, enough that you will corrupt the data in those cells. So clearly, if you refresh DRAM much more frequently, then you can solve this problem. But that's not a good idea because we want to get rid of refresh. Remember, that's not good for scaling. That's not good for energy. That's not good for performance. So what is worse about this is actually a user-level program can exploit these errors. Basically, this is when we wrote the paper in 2014, we released this code. It's only a 6-line x86 code, which basically selects address X and Y, and basically hammers those rows where address X and Y sit. It avoids cache hits, it avoids row hits, so that you actually go to memory directly, and it basically does this. It ping-pongs accesses to X and Y. And then if the chip is vulnerable, you'll get errors. Now this is nice, and we showed that you can actually do this with this user-level program on Intel and AMD, but it doesn't matter. All of the memory, as long as you have a chip with a memory controller that's able to activate the rows at a certain frequency, then you can actually do this. And all memory controllers are actually capable of this. And this is a real reliability and security issue because of this, because a user-level program can cause these Bitflips, and when we wrote the paper, we said that you can hijack a computer by this, you can crash it, you can do a lot of things. And that was the first thing that we said in the paper, actually. Memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in another address. I still believe this. I think this is very fundamental. While we were working on a security exploit, the good folks at Google Project Zero were very good at finding these security holes. They actually took our work and it basically showed that you could gain kernel privileges by exploiting this row hammer problem. The next slide is essentially copy and paste from different parts of this blog post, which I would recommend you to read. It's by Mark Seaborn and Thomas Dulien. It's a beautiful blog post. It's beautiful security engineering. It basically says that they learned about the row hammer problem from our work. They tested a selection of laptops and found a subset of them were vulnerable to the problem, and they built two working privilege escalation exploits that use this effect. One of them I'm going to ignore. It basically takes over the Google native client. But the second one is very serious. It basically, with a lot of security engineering, it causes these row hammer-induced Bitflips and gains kernel privileges on x86 for Linux at the user-level process. And the way they do it is essentially they target page table entries. They're able to induce page table entries of a process, of this user-level process, in the entries that point to the process's own page table, and they're able to gain write access to their own page table by doing this. Of course, it sounds easy, but it's really a lot of good security engineering to be able to do that. Now, once you gain write access to your own page table, all bets are off. You have all types of access to any type of memory base, the entire system essentially. And people started drawing pictures like this, basically, is at the end of memory. I like this particular explanation really well. That a very famous hacker on the internet basically said that row hammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door that you're really after. So you can keep banging on these walls, and then that door will magically open, hopefully. If you're stuck in this room, of course. So, okay, people built a lot of interesting attacks. I'm not going to go through this. These folks showed that, from TU Graz, showed that they can gain unrestricted access to systems of website visitors by inducing these attacks through JavaScript. This is one of the very interesting ones. These folks showed that you could actually, you could probably download their Android application. They basically showed that you could hammer an Android and they could deterministically take over this cell phone by exploiting the deterministic memory allocation patterns that the Android memory operating system has, because they were able to fool the operating system to allocate a page table entry to a location that they determined previously was vulnerable to row hammer, and then they hammered that location to gain access to the entire system. And they show that you could do this on ARM processors on many, many cell phones. And other people show that you can execute these attacks through the GPUs, and then you can do these over the remote direct memory access protocol, and there are other ones. And this could be one other attack, of course, if you're tired of these Bitflips in your computer. This could be a solution also, but I wouldn't recommend it. So what's the solution? Let's talk about the solutions very briefly, because this is going to motivate the intelligent controllers as we expected. Today, we don't have intelligent memory control. The intelligence in the memory control is very, very little. Actually, the configurability in the memory control is very, very little. You can change the refresh rate slightly. And that's exactly what the industry adopted. We actually analyzed in our paper solving the problem by increasing the refresh rate. And we said that it's not a good idea because it increases your power and energy. And if you want to get rid of every single row hammer bit flip that we've seen in our experiments, you need to increase the refresh rate by 7x. And industry actually adopted that solution, which makes sense because there's no other way around it. You could do it in software, but it's a lot of overhead, I think. So they basically increase the refresh rate. This is Apple's solution. Other folks also adopted it. The downside is that they don't say exactly how much they increase the refresh rate by. It's not clear if the errors are actually completely gone. There are other solutions to the problem which I'm not going to go into, but I'll give you an example of our solution, because our solution is an example of how you can design a slightly more intelligent memory controller to overcome these deficiencies. Our solution is more probabilistic. Basically, the memory controller, after it finishes activating a row, when it's ready to close that row, it activates physically adjacent neighbors with very, very low probability. And you can adjust the probability depending on your paranoia level in terms of attacks. So it's configurable. And this gives you a very good reliability guarantee. And we show that it's actually low cost and low complexity. It's essentially stateless. It doesn't even need to be random, but I'd be happy to have that discussion later on. So it's an effective solution. And you could actually implement the solution in the DRAM chip or in the memory controller. DRAM chips today implement a slightly modified version of this solution that's not perfect in my opinion, by exploiting the slack and the timing parameters in the DRAM chip. So there's a lot of slack in the timing and refresh parameters of DRAM chip today. For example, the data sheet of DRAM says you need to, after you do an activate, you need to wait for, let's say, 15 nanoseconds to send a read command. That's actually not true. You could actually send the read command 5 nanoseconds later if you know what you're doing, and you would get the correct data. There's a lot of margin timing slack because timing slack is determined based on the worst case parameters. So they actually, DRAM manufacturers exploit this timing slack so that they can sneak in some refreshes to solve this problem. I don't think this is a very good solution because we actually want to get rid of that timing slack to reduce the DRAM latencies. That's actually a very good area where you can reduce the DRAM latencies. You could implement this in the memory controller. In this case, memory controller becomes slightly more intelligent. But of course, there's a downside over here. You need better coordination between memory controller and DRAM. Today's memory controllers don't know the topology of DRAM. They don't know which rows are adjacent to each other because that information is actually kept secret by the DRAM manufacturers for some reasons, which I'd be happy to talk about also separately. So this information needs to be communicated. And this is a call for having more information communicated between the memory and memory controller so that memory controller becomes more intelligent so that it can solve some of these issues. I believe this is really the right place to implement solutions. And actually, there's hope that's happening. So this is one of the latest BIOSes from Intel processors. In some of the Intel memory controllers give you an option in the BIOS to pick your solution for row hammer. You can either pick the hardware row hammer protection or 2x refresh. And if you go to hardware row hammer protection, it's a modified version of probabilistic adjacent row activation. You can choose your probability at which you can activate, issue additional activates to solve the row hammer problem. Sorry, the screen is not very good, I think. I don't know why. Maybe it's because of the VGA, but these slides will be available. So you can see that you can actually do the row hammer activation every 1 out of 2 activations, or you can go to 1 out of 2 to the 15. Of course, clearly there's a performance curve over here that you can figure out also by playing with this. Okay, I'm not going to talk about row hammer more. If you're interested, we've written a lot of papers about it. This is our original paper. This is a more forward-looking paper, and this is a recent retrospective we wrote on the special issue for TCAD, for hardware security. So there's a lot more to come, I think, in terms of row hammer, but it's going to be difficult to launch attacks, but other kinds of issues like this will come. And as I said, industry is writing papers about it too. I'm not going to talk about this in more detail. They didn't talk about row hammer in this particular paper because it was not exposed at that point and yet, but they knew that there would be problems like refresh that could be solved by having more intelligent memory controllers. And we actually designed intelligent memory controllers in other domains. So in SSDs, for example, we have very intelligent memory controllers. SSDs actually overcome a lot of these circuit level and device level scaling issues by having intelligence inside the memory controller. Basically, the proposition is that we should have such intelligence in the DRAM controller also. It's going to fix a lot of the circuit level and device level scaling issues. Of course, we need to be much more careful because the DRAM is much faster than SSDs. And if you're interested, there's a lot of work that we've done on SSDs also. So the first takeaway, looking from the device level and circuit level, if you want to scale, we need intelligent memory controllers. Okay, now I motivated from the bottom up. Now let me motivate from the top down. Top down will actually be probably easier because top down we're having a lot of problems with scalability also. In the end, in my opinion, it's all about scalability and efficiency. If you want scalability and efficiency, we want to have more intelligence in the memory controller. So if you look at the top down, there are three key system trends. Data access is a major bottleneck. This was actually brought up by Sada yesterday a lot in his keynote. Energy consumption is a key limiter, and data movement energy dominates compute. This is especially true for off-chip to on-chip movement. Clearly, we need more memory performance for many applications. In my opinion, the high-level picture, maybe it's a longer-term picture, is this. Do we want a world that looks like this, or do we want a world that looks like this? I think this was also brought up by Sada, saying that computing is consuming a lot of power going into the future. And I think we might end up with a world like this. And if you actually go back to Maslow's human hierarchy of needs, he really did not say reliability and security is the first thing. He said your physiological needs are the most important thing. And you can think of everlasting energy as perhaps the most important thing. If you don't have energy to live, who cares about your security and reliability? And the future, I think we want a future that's high performance, that's energy efficient, and that's sustainable. We want all of them at the same time. We don't want that idle picture of green fields without having high performance. So the question is, how do we get all of them at the same time? And the problem is that data access is the major bottleneck that we have today, and our current principles cause great energy waste. They also cause great performance loss, but I put this in parentheses because we do a lot to mitigate that performance loss. We build a lot of hierarchies, we build a lot of mechanisms, and that all comes at the expense of even more energy waste. In my opinion, we're in this vicious cycle right now, where because of the way we're designing these systems, fundamentally, we're causing great energy waste to mitigate, and we're causing great performance loss. To mitigate that performance loss, we're increasing the complexity of the system, and we're causing even more energy waste. We need to break that cycle if we want to be sustainable in the long term. And if you want to point out the problem, I think the problem is really we're processing data far away from the data. And if you go back to the fundamentals, this is von Neumann's original paper, a computing system consists of three major components: computation, communication, and storage. And over the course of 70, 80 years, we've optimized the computing unit quite a bit. But we haven't really optimized the communication and other units as much. Basically, we're designing systems to be very processor-centric. And when I think of processor, it's not only just the processor, it's also the accelerator. So GPUs, any type of accelerator that you can think of, they're all processors to me. We're very centric from that perspective of those processors. All data is processed there, the processor is heavily optimized, and data storage units are mostly dumb, essentially. Yet we know that we have a problem with performance for a long time, actually. This is a quote from Dick Sykes, who was the chief architect of Alpha. And after he designed, his team designed the Alpha 21164, he wrote this one-page paper in Microprocessor Report. I would definitely recommend this paper. And in this paper, basically, he said that we designed this processor to finish 4 instructions per cycle, every cycle, but it's finishing 1 instruction every 4.8 cycles on this important database workload, data-centric workload. And basically, it's operating at 1/18 of its peak bandwidth. Why? Because it's waiting for memory. And I don't have this quote over here, but basically, he ends this paper by saying that in the future, memory system design is the only issue that's important for microprocessor design going forward. I don't know about the only part, but he was very strong in terms of the only part. I'd recommend you take a look at the paper. Okay, fast forward 10 years later, this is my own PhD thesis. We looked at basically tolerating memory latencies with efficient techniques in the processor, and we analyzed all of the workloads that Intel used to design its processors with at the time. And basically we saw the same thing. Most of the time the processor is waiting for cache misses, memory. Okay, you don't believe Dick Sykes, you don't believe me, since everybody believes Google these days, maybe not in China, but everybody in the US believes Google these days. Google published this beautiful paper in ISCA 2015, where they actually looked at all of their data center workloads according to them. And they did a very similar study, and they basically showed that most of the time the processor is waiting for data. It's doing useful work only 10 to 20% of the time. And they have a lot of beautiful analysis of their own data center workloads, and they show that most of the time the processor is essentially waiting for data. Okay, so this shows you a picture of just the last 20 years or so, and in the last 20 years or so, nothing has changed. The processors are becoming higher performance, but they're still waiting for data. Clearly the processor performance improved, but they're still waiting for data. So essentially we have a processor-centric design, and this is really a grossly imbalanced system. Processing is done only one place. As a result, data moves a lot. And this is energy inefficient, low performance, and complex. And the reason we're improving performance is because we're increasing the complexity and load that we have in the processors and the accelerators so that we can tolerate the data access from memory. We have complex hierarchies and mechanisms. Sarai talked about compilers. In regular cases, perhaps compilers can do a really good job, but we're increasing the complexity in the compilers also. But in irregular cases, we have actually not a lot of choice, in my opinion. So essentially, we have a lot of energy inefficiency, low performance, and complexity. And as a result, we're stuck with a picture that looks like this. Most of the system, more than 90% of the real estate of the system is dedicated to storing and moving data. We call this a computing system, but it's really not dedicating itself to computing. It's really a data storage and movement system in the end. Okay, let me give you the energy perspective very quickly. This is data that I borrowed from Bill Daly. It's old data. So you can argue with all of these numbers over here. Basically, we look at the cost of a double precision floating point operation is 20 picojoules. A DRAM read or write is 16 nanojoules. So if we exaggerate this a little bit, a memory access consumes 3 orders of magnitude more energy than a complicated floating point operation. Okay. So if you don't believe that numbers, there are other numbers that suggest that this is actually about 2 orders of magnitude more energy consumption in memory compared to an addition. Actually, I was at DAC, the DAC conference in June recently, where people were talking about the memory access versus computation costs of their AI accelerators at that time. And one of the folks who was designing an AI accelerator threw out the number that a DRAM access in their accelerator consumes 160x the energy of a floating point multiply and accumulate, essentially. So we're stuck with essentially 2 orders or 3 orders of magnitude more energy with a single DRAM access compared to a complicated operation in the CPU. As a result, we have this picture basically. On important workloads, more than 60% of the energy, entire system energy is spent on data movement. But we don't want to move data. If you want to be efficient and sustainable high performance, we really don't want to move data. So what do? Essentially, in my opinion, we need a paradigm shift to enable computation with minimal data movement. Compute where it makes sense, where the data resides. I'm not suggesting compute only in memory, only in storage. We really need to enable these different parts where data is stored to be able to compute on the data that they store. So it could be the caches, it could be the interconnect, it could be the memory controller, it could be the network controller, it could be the disk. And I believe it needs to be done in all of those, and we really need to start step by step in all of those places. So this means that we need to think of computing architectures more data-centric. So this is really a mindset shift, in my opinion, because once you start thinking of things as data-centric, you start finding more opportunities on how to really reduce the energy in the system. Okay, so the goal, I will talk about processing in memory in the rest of the talk. But as I said, memory is one component of where processing should be done. In my opinion, memory is one of the hardest components because there has been a very strong dichotomy between processing and memory. And we really didn't help ourselves by increasing that dichotomy over the years in both industry and academia. So what do we want to do? We want to essentially put important workloads in memory, and we want to be able to query memory. Ask the memory question, can you execute this function for me? If the memory says yes, it executes the function and returns results or partial results, and then the accelerator and the processor can do more stuff on that memory. So today we don't have these interfaces to be able to satisfy this. So there's some very high-level questions that I'm not going to answer all of them. I'm going to give you examples. But these are high-level questions that need to be answered in my opinion. How do you design the compute-capable memory and the controllers? How do you design the processor chip and the in-memory units? How do you design the software and the hardware interfaces to be able to do that? We do not have the interfaces to be able to do that today, neither in software nor in hardware. How do you design the system software compilers and languages? And how do you actually design the algorithms at some point to actually take advantage of this data-centric paradigm? In my opinion, there should be also theory. I think Sarai also touched on that theory part a little bit. We don't really have the theoretical background to actually understand computation as a data-centric computation parameter, because we really develop all of this theory as a processor-centric theory over the course of 70 years. Okay, so clearly this requires a lot of effort across the stack, and there's opportunity for all the way from devices to algorithms, in my opinion. I'm not sure about the electrons. I don't know, maybe you can make the electrons more data-centric also, but I haven't thought about that. And clearly my background doesn't allow me to think about that at this point. But there's a lot of opportunity, and in my opinion, this is a very fresh research area to look into. Okay, let me summarize this part, and then we're going to talk about how to do the in-memory computation. Basically, I think in-memory computation is an old idea. It's been proposed since late 1960s. The earliest paper on the topic is by Harold Stone in 1970. It's called A Logic in-Memory Computer, and then it basically appeared in many, many other papers over the course of the years, and it never materialized. I think today we're in a unique place because technology is pushing us to have intelligent memory controllers, and actually manufacturers are experimenting with different types of memories that can do some sort of computation. We're going to talk about the 3D stack memory. There are limited forms of processing inside the row buffers, and that automata processing over there. And also, we're at a very unique place today that applications are not scaling because of this data movement issues that we have today. Okay, but even though past has explored some of these technologies for in-memory computation, I believe it's going to be very hard to take a general purpose processor, put it inside a DRAM chip, and make it work. For multiple reasons, these technologies are very different from each other, and if you want to put a general purpose processor inside the DRAM technology, or any type of memory technology, you're going to have to deal with the issues of leakage, and that processor is going to be slow, and you're going to increase the cost a lot. So we need to think differently in this direction also, in my opinion. I'm going to talk about two ways we can think differently. The first one I really like a lot. It's surprisingly not a lot of thought has gone into it for a long time. So the first approach is minimally changing memory to do very specialized operations at very high performance and efficiency by exploiting internal connectivity to move data, by exploiting analog computation capability. I'm going to give you examples from DRAM, but you can think of examples from different memory technologies like RAM or memristors, and there's actually work that built on what I'm going to describe to do it in RAM. Let me talk about data copy initialization very quickly. One of the things that we can do in DRAM today is data copy initialization, and this is actually used by many, many system components. Operating systems use a lot of these actually. We don't have a lot of time, so I'm not going to go into the software components over here. But Google, in the same paper that where I showed data from, they said that just the system calls memmove and memcopy occupies 5% of the cycles in their entire data set. It's a lot for just 2 system calls to occupy. So how do we do bulk data copy today in our systems? If you want to copy this white page to that gray page, we go through the processor. And you see the processor-centric mindset at play over here. You basically have high latency, high bandwidth utilization, you cause cache pollution, but you could eliminate that through the BMA engine today. Unwanted data movement. Basically, by going through the processor, we have a long latency for a 4 kilobyte small page copy. We actually have 1,000 nanoseconds. Even if you do it through the BMA engine, you don't go through the cache hierarchy. It's 1,000 nanoseconds and 3.6 microjoules. Now, wouldn't it be nice to give the system an option? And the option is that the CPU tells the memory controller to do the copy, and memory does the copy, doesn't disturb anything else in the system. Now, this is low latency, low bandwidth utilization, no cache pollution, and no unwanted data movement. I'm going to show you quickly a mechanism that reduces the 1,000 nanoseconds to 90 nanoseconds in the unoptimized case, and 3.6 microjoules to 0.04 microjoules in the unoptimized case. If you optimize it, you can do even better actually. And the idea is very simple. We call it row clone. If the source and destination are in the same DRAM subarray connected to the row buffer, basically you just need to do 2 consecutive activates. You first activate the source page, which brings the data into the row buffer, sends amplifiers, and then you activate the destination page, which implicitly deactivates the source page, and the data that was brought into the row buffer from the source page gets copied into the destination page. And this works because of charge sharing principles that we have in DRAM, and because of the fact that the sense amplifiers are very strong and they can drive the DRAM cells. Of course, we need to generalize it. I'm not going to go through how you generalize it within a DRAM chip, but there are ways to generalize it with very, very low cost. And the cost is actually very negligible for this particular case. And the benefits are relatively high. You can see that the latency of a page copy reduces by more than an order of magnitude, and the energy, memory energy of a page copy reduces by almost 2 orders of magnitude. If you actually optimize it, you'll get to 2 orders of magnitude. Okay, so you can actually do this with very low cost in memory chips. That's true for any memory chip actually, not just DRAM. So the mindset is we're thinking about memory as an accelerator. We're designing all of these accelerators on the processor-centric paradigm. But why don't we think of having an accelerator, more like a conventional accelerator that's good at doing some things, on the other side of the memory bus, on the right side. I think this actually has a lot of efficiency because it has access to this large store, low latency and high bandwidth access to that large store. Let me give you another example of what we can do. Basically, this was the in-DRAM copy. In-DRAM 0 or initialization is another example, but I'm going to give you an example of AND, OR, NOT, and majority at low cost. Basically, we can exploit the analog computation capability in DRAM by activating multiple rows. And this leads to significant performance improvements. I'm going to give you the key idea in a little bit. I believe new memory technologies have even more opportunities because DRAM fundamentally is crippled in the sense that if you want to do anything to a data, you need to read the data. When you read the data, you destroy the data. That's not true for emerging non-volatile memory technologies. And you can actually do even more with even more minimal data with these emerging memory technologies. I'm not going to talk about that. There's a lot of work in this area. I believe there needs to be even more work, especially with the integration from the software side. Okay, so how do you do this in DRAM? If you actually look at these 3 rows, A, B, C in DRAM, I'm going to show you an example of a single bit line, a single cell. But think of an 8 kilobyte row, and think of having the ability to do this in 1,000 different subarrays in DRAM. So you can do this on 8 million bits. Let's take a look at the primitive. The primitive is triple row activation. You have the ability to concurrently activate these 3 rows. Now, if you actually do that, what you get is based on the charge sharing principles is a majority circuit. If at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So the final state is bitwise majority. Now this is good because you can actually change your algorithms to implement everything with bitwise majority. Now that's not easy. Some algorithms are good fit, but not all algorithms. So the realization is that you actually take out C. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now you can do AND and OR, bitwise AND and OR in DRAM across many, many subarrays. Now, of course, AND and OR is not enough. We wanted NOT also so that we can be functionally complete. Now we can express any algorithm with this. So NOT is not as easy. I'm not going to go through the details, but basically you take the negative value on the other side of the sensifier and feed it back into a special row. It costs a little bit more in DRAM, but you can do it. Now you can do AND and NOT in DRAM, which means that you have a functionally complete DRAM. It's bulk bitwise, so it's not efficient for operations that do not exploit this bulk bitwise model, but you can essentially convert any of the algorithms to this model. You need to think differently though. Okay, so what is the benefit? I'm going to skip this one. But basically, you get significant performance and energy improvements compared to DDR3. So NOT actually has the highest performance, AND and OR, and then you can build NAND NOR, XOR, XNOR, and then for whatever definition of mean, you can actually compute a mean. But it's basically 30 to 60x improvement in terms of performance and energy. Now the question is, who takes advantage of it? Clearly, if you want to make the best use of it, your applications should be a good fit or can be easily rewritten to be a good fit for this paradigm, which means that they need to use bulk bitwise operations. A lot of databases, bitmap indices are actually built for this. This bitweaving database from Jignesh Patel's group is actually designed for bitwise operations, maximizing bitwise operations to do column scans so that they can do this efficiently on GPUs. That's also a very good fit. Microsoft designed this bitfunnel engine that's actually a very good fit with the same mentality. They wanted to increase the bitwise operations they do so that they can take advantage of the parallelism in the GPUs and the FPGAs. And there are a bunch of other things that I'm not going to talk about. I'm going to give you examples from the bitmap indices. I'm going to skip the slide again. On your own time, you can take a look at it. But basically, we ported a bunch of bitmap indices that databases use, and we see significant performance, end-to-end performance improvements in query latency. It's 5 to 6, 7x in terms of the latency reduction in queries. If you actually take the database that I mentioned from, it's called bitweaving, and you actually port it to our substrate, you get significant performance improvements in query execution times also. It's 4 to 12x. And the good news is, if you increase the data set size, the performance also increases, scales, because you can actually parallelize this across many, many subarrays in your DRAM module. You're basically limited in the end by the capacity that you have in DRAM and the power at which you can power these operations. Because in the end, you're doing computation in DRAM. Again, the mindset needs to change. Sometimes when you write papers in computation in memory, people say that, yeah, but this increased power in DRAM. Yeah, sure, you're doing computation in DRAM. You have to have a heatsink on your DRAM now, not on your processor, perhaps. Okay, so if you're interested, this paper has a lot more detail. And we recently written this summary paper with my student whose thesis was on this topic, who's now at Microsoft Research India. Okay, so let me switch gears and talk about another opportunity, which is 3D stacked memory. This is a different way of thinking. It's not about minimally changing memory chips, it's exploiting an opportunity which already exists. And the opportunity is that DRAM manufacturers are already designing these 3D stacked logic and memory layers that are connected to each other via some sort of interconnect. Today it's through silicon vias, high bandwidth, low latency, but in the future I believe it's going to be even more interesting through three-dimensional technologies, like monolithic three-dimensional technologies, that's going to enable even more interesting things. And if you look at this paper that we written in 2015, that we already have a lot of 3D stacked memories, or memories that can be 3D stacked if we want them to be. So when we first started looking into this, we had two key questions that we wanted to answer. Basically, how can you use this 3D stacked memory as a coarse-grained accelerator to actually improve performance and energy efficiency on really important applications by changing the entire system? You have no limits. Or by doing simple functional floating, you have some limits. Or you have a lot of limits without changing the system and programming and virtual memory and coherence much. I'm going to give you examples of this as much as time permits, and then we're going to conclude. So we looked at all of these, and I believe there are a lot of other explorations that need to be done in this space. So this is maximally changing the memory system and minimally changing the system. Let's talk about maximally changing the system. And again, I think that the potential is even more than what we've done, because you can optimize the system even more. We didn't optimize the system enough, I think. And when we first started, if you really want to maximally change the system, you really need to specialize for applications. And when we first started looking into this, we wanted to look at graph processing, because graph processing is actually, graph analytics is very fundamental to many, many algorithms that we have, many, many frameworks that we have, like social networks. But it's not only social networks, bioinformatics, and many, many other, machine learning also is actually, fundamentally has a graph processing layer. But if you want to scale graph processing, large-scale graph processing is challenging. By throwing cores at it, you get some performance, but not scalable performance, and you get a lot of energy overhead. Why? Because if you look at a lot of graph algorithms, there's a significant chunk that has frequent random memory accesses with little amount of computation. And this clearly exercises this huge energy bottleneck that we discussed, right? You do a lot of memory accesses for a very little amount of computation, then why are you actually bringing all of those memory to the processor to do that very little amount of computation? Because you're not amortizing the energy cost. So this is the system that we designed to overcome this. Other people have improved upon this system. There are actually a bunch of papers that have improved on the system. But I'm going to talk about the basic idea. There's a lot of stuff in the system that I cannot go over, but the papers over here. Basically, we started with these 3D stacked logic and memory chips, and we interconnected them so that we can get very high capacity. And if you look at a single memory chip, it consists of these vaults, and each of these vaults has a memory controller, and they're interconnected with each other, so they can communicate with each other with some sort of network. In addition to the DRAM controllers, so DRAM controller controls the stack of memory on top of it, and the memory is partitioned across those controllers. You basically put very simple in-order cores so that you can do computation on the data that's on top of you. And we designed the system so that graph nodes are partitioned on top of these different chips, and they're also partitioned on top of these different vaults within a chip. Now, if you want to operate on a graph node, you send a message to the core that houses that node. Essentially, you move the computation to the data, not the data to the computation. And in this case, we had the extreme. We always move the computation to the data. You can explore the space even more. Basically, it's a message passing system. You send remote function calls to the cores that house the data that you try to operate on. And we added some prefetching mechanisms because we actually have a lot of bandwidth that's exposed to these in-order cores that cannot be exploited by the in-order core by itself. So we actually exploited that bandwidth by adding graph processing specific prefetching mechanisms that I'm not going to talk about right now. So let's take a look at the performance results of the system. There are clearly a lot of design choices. So if you squint a little bit, this is actually very similar to parallel processing systems of the 1980s. For example, if you remember the J machine and a lot of the other parallel processing machines, this is very similar, except it does processing in the logic layer. So a lot of the design choices that we made in the end resemble the message passing systems of the day. Okay, so we compared this to the systems that are baselines, hybrid memory cube, that mini core that is 640 gigabytes per second. If you look at the system that we designed, it's Tesseract. It doesn't look like any of these systems because it doesn't have the processor memory dichotomy. Memory and processor are integrated together in these 3D stacked logic chips. And as a result, you get 8 terabytes per second bandwidth exposed to the cores. That's a lot of bandwidth. And as a result, you get significant performance improvement on an average across 5 different graph processing algorithms. You see it's about 13 to 14x over here. And again, we didn't optimize the system. I believe by optimizing the system, you can do even more. And as you can see over here, we're able to consume 2.9 terabytes per second out of 8 terabytes per second. So we're not very efficient. I believe we can improve the efficiency even more. So if you look at the baseline system, it is able to exploit 80 gigabytes per second out of 104 gigabytes per second. So the baseline system is actually much more efficient. than us. So I believe there's a lot of room for improvement to increase that 13x to maybe 40 to 50x. And the energy reduction is actually commensurate. You get 8x energy reduction compared to the baseline, even if you discount the out-of-order cores in the baseline. So I believe there's more to do, but this is really changing the entire system. We got rid of cache coherence, we got rid of virtual memory. You can think of this as a primitive form of GPU. Essentially, you offload the computation, graph computation, to this specialized accelerator that does the graph computation for you. I think there's a lot more to do in this area so that you can improve the programmability of the system. Let me give you an example from the work that we've done with Google very quickly, and then I'm going to talk about adoption, and then we're going to conclude. So let me talk about this. Our next step was actually, what if you don't want to change the entire system? You want to do this, you want to identify simple functions, and you want to actually offload those functions to this 3D stack memory. What are the functions, and what kind of benefits you would get? Clearly, the benefits are not going to be as high as 13x, 14x in this case, but they're going to be still significant. So what we did was we analyzed these 4 different workloads that are actually used in many, many mobile devices, and they're very memory bottlenecked in the end. And we wanted to quantify the energy cost of data moment. I already gave you this data. Basically, more than 60% of the total system energy is spent on data moment across the memory hierarchy, and we wanted to examine processing in memory, moving computation close to data at a function level. The challenge here is limited area and energy budget. Especially if you have a system like this, you need to be even more careful compared to a server system. And that's essentially what we tackled in this work. So our second key observation was very interesting, I think. If you look at these workloads, a significant fraction of the data mode often comes from very simple functions. I'm going to give you examples of these functions. You can actually ship these simple functions to memory to either small low-power cores or to small fixed function accelerators. In my opinion, having a reconfigurable logic layer is the best, so that you can reconfigure the logic layer to implement your fixed function accelerators. And we showed that offloading these simple functions to memory actually increases your performance and energy efficiency by more than 2x, let's say. 55%, it's really 2x in the end. So when you write the paper, it's better to say 2x. In the paper, we said 55% reduction in execution time, which is 2x performance improvement, but we could have done better, perhaps. Let me give you an example of these functions. I'm going to pick the machine learning, since it's interesting, but this is inference. If you look over here, I mean, we looked at TensorFlow, and we found out that more than 50% of the inference energy is spent on data movement, and 2 functions are responsible for a good chunk of that inference energy. Essentially these are data manipulation functions, packing and unpacking of data, essentially data reorganization, and quantization of data so that you get higher energy efficiency. So packing very quickly, basically you reorder the elements across different layers of the network. You need to change the ordering of the elements so that each layer is efficient in terms of how it works on the elements. And that packing and unpacking consumes a lot of energy and execution time in TensorFlow. And if you look at this, this is a very simple data reorganization process that requires very simple arithmetic. So this is a perfect fit for offloading to simple units in memory. Okay, quantization is also another simple thing. This is done by all networks today. Actually, you basically quantize your large data to very small data elements, floating point to integers, so that you can improve execution time, energy consumption. And we found out that this actually consumes significant energy and execution time, and most of its energy and execution time comes from data movement. And again, this is a very simple data conversion operation that requires very simple arithmetic operations. And if you offload those, you essentially get significant performance and energy improvements, as you can see over here. Basically, we did this for the browser, so you can see that there are functions that are interesting, like compression and decompression, texture tiling, colorability. We did this for video playback and capture, and there are a bunch of functions that are over here that are also interesting. And if you offload these to simple cores or specialized accelerators in memory, you significantly reduce the energy. And you can see that the specialized accelerators reduce the energy even more clearly as expected. But on average, it's about 2x, a little bit more than 2x. And runtime also reduces, as you can see over here. It's again, on average, it's about 2x. Okay, so it's not 13x, it's about 2x, but again, maybe this is a good place to start. Okay, and we also looked at GPUs, but I'm not going to talk about these in detail. These slides will be available. Let me talk very quickly about this minimal thing, and then we're going to conclude. So a minimal thing is very interesting because what can you change minimally in the system without disturbing anything else by not giving up the programming model? I'll give you the basic idea and the results, and then we're going to move to adoption very quickly. Basically, the idea over here is if you want to not change the system, you add an instruction. And that instruction can be executed either in memory or the processor. That's the idea of PIM-enabled instructions. And this instruction has a lot of restrictions. It's cache coherent, it's virtually addressed, it operates on a single cache block. Now you get rid of the data mapping problem because the cache block exists in a single memory module. You don't need to worry about the case where this instruction needs to operate on multiple different things, and the cache block is already within the page so that you can translate things in the processor. So it looks like an instruction like this. And this requires no changes to sequential execution and programming model, no changes to virtual memory, very minimal changes to cache coherence to ensure that you're operating on that block and nobody else is touching it at that point in time, and no need for data mapping, as I said. And the second key idea is you need to figure out where to execute this instruction. And this is really important because if you always execute in memory, you sometimes lose performance. If you always execute in the processor, you'll sometimes lose performance. You really need to decide where to execute based on a performance model. And I think this is also a slide I mentioned that I believe performance models are going to be even more important for runtime systems that we design for processing in memory going forward. Okay, so I'm going to skip this. You can animate these yourselves if you're interested, but basically this shows the value of this. And so these are the instructions, some example instructions. So the question is, who designed these instructions? Again, I believe a reconfigurable substrate is a very good idea in memory for this. But you can see that a dot product is an example. This is a machine learning application, support vector machine. Euclidean distance is another example. This is stream clustering application. You do streaming analysis on data. So clearly there are some specialized instructions that can buy you a lot of performance. So what is a lot of performance? I'll give you that. Basically, on large input data sets, you get about 47% performance improvement. Again, it's not 13x, it's not 2x, it's 47%. But you do relatively small changes to the system in this case. And the energy reduction is also commensurate. For large data sets, it's about 25%. And this also shows a small and medium. But small and medium data sets are not as interesting because caches are very effective in those. And as a result, you can actually, you don't gain a lot from processing in memory, but you get some from processing in memory in medium data sets, as you can see over here. Okay, if you're interested, this paper has more detail. So let me talk about, okay, basically we have a huge challenge and opportunity for a feature. How do we design the computing architecture for minimal data load? And processing in memory is very interesting, I think. But we have an issue, and this is an issue with any new technology, and I believe we need to look at the adoption of processing in memory. I'll list some adoption issues related to processing in memory over here. Basically, we need to somehow understand the functionality and application of software for processing in memory. I think this is really important. If you just develop hardware and not think about the software, then there's a big problem, because that technology may be useless for everybody in the world. We need to think about ease of programming, interfaces and compiler and hardware support. That's really critical. System support is critical, as I said, especially if you want to make it general purpose going forward. GPUs are actually a very good example of this. Over time, they became more programmable, and they started adding system support, as you can think about it. And we need mechanisms for runtime and compilation systems for adaptive scheduling, data mapping, and access and sharing control. And I believe we need infrastructures and models to assess benefits and feasibility. I believe this can be solved with a change of mindset. Basically, we need to change our mindset so that we actually are tackling these problems. And I believe we need to revisit the entire stack, but we can start step by step. And there's a lot of opportunity across all of these layers, in my opinion. It's not just one layer or two layers, it's really across the layers. Okay, so if you're interested, we actually have a bunch of papers that talk about some of these open problems also. And this is one of the more recent papers that's going to appear on this IBM Journal of Research and Development special issue that talks about especially workload and programming ease perspectives of processing in memory. So there's some of these slides cover some of these adoption issues, so I'm going to skip them. But hopefully they'll be useful for some people who are interested. But let me conclude. Do we have time to conclude? Okay. We have time to conclude. This is the most fun part of the talk for me. So hopefully it'll be fun for you also. So, okay, a famous architect says architecture should be based upon principle, not upon precedent. Does anybody know who this architect is? This guy is a real architect, actually. He's Frank Lloyd Wright. He's probably the most famous American architect. And he didn't design this in the middle of Pennsylvania. Instead, he designed this. Which this picture doesn't do justice to it. This is really falling water. This is masterpiece. And it's really on top of this waterfall. It imitates this waterfall. So it's based on a principle. It came at a much higher cost compared to this thing. This was very cheap. This was very expensive. But this is new technology. Once you transition to the new technology, you don't think about how cheap or how expensive it is, right? You just use the new technology. So now people go to here, they don't think about the cost of it. But when this was being built, the Kaufman family who commissioned it, they basically had to tell Frank Lloyd Wright, okay, you're done, we're not paying you more money. Okay, so this is a good example of processing in memory perhaps. So you need to pay the cost to transition to the new technology. And once you transition to the new technology, it's a whole new world. And there's a principle behind it. And now that I'm in Zurich, I don't use the thing that's close to Carnegie Mellon. I use these train stations that's all over Europe. These are actually not bad. These are functional. They work. That's true for the other simple shack also. But they're nothing like this. This is a train station in Zurich, Stalenhofen. That's amazing. It's also similar to this train station, Lisbon. It's also based on some principle, as you can see, that's the blueprint. It's also similar to this City of Arts and Sciences in Valencia, which you may actually experience if you go to ISCA next year. And this is also similar to this thing in New York. Now, I couldn't find an example in China over here. Maybe we'll find something in China in the future also. But this architect doesn't come to China as far as I know. But this is in New York. I'm sure some people have been there. This is called the Oculus. It's designed by Santiago Calatrava, who's an ETH alumnus. And it's based on some principle. But this is, again, new technology. If you look at this, this cost New Yorkers $4 billion. And there was a lot of debate while this was being built. They said, why are you doing this? And in the end, $4 billion was not enough for everything that this architect wanted to do. But now the transition to the new technology is complete. People go there and look at the place in awe. They don't think about the cost. And the new technology works really well. Okay, and it's based on some other principle. So the key question I have is, do we have the overarching principle for computing? I don't claim to have them, but I know for sure that processor centricity is not the only principle that we should be exploiting in designing our systems. And we're designing all of our systems as processor-centric, with the processor-centric principle today. So I believe it's time to design more principled system architectures to solve the memory problem, because memory problem is going to get worse. And we need to be more balanced, high performance, and energy efficient. And we're actually violating all of these three key things over here. If you take a systems course, the first thing that says you need to have a balanced system design. Processor memory dichotomy is not a balanced system design. And if you want to have a balanced system design, we need to be more data-centric or memory-centric. This means that we need to enable computation capable inside and close to memory, and also all of the other places where data resides. And we need to take advantage of it. I believe this can lead to orders of magnitude improvements. I've given you some examples of this. They're by no means the end of it. This can enable new application and computing platforms that we may not be imagining today. This can enable better understanding of the nature, because nature is probably more data-centric than we think of. And who knows what else. So I believe regardless of challenges, there's a lot of hope. But we need to think across the stack. And I believe we need to think so that we think from the adoption perspective also. So I'll give you some hope also. Maybe this is not the best example, but this is an example of where a very costly technology revolutionized our lives. And if I look at this thing, there's only one technology that I can point to in terms of electronics, and that's flash memory. I think flash memory over here, for decades and decades and decades, it was a very emerging, doubtful emerging technology. I was at the Flash Memory Summit recently. From 1960s to 1990s, flash memory is very doubtful. I know of people who were writing NSF proposals in 1980s, who are friends. They were basically working on something called garbage collection for flash memory. And they were getting rejections saying that, who cares about this flash memory? Why do you want to do garbage collection for flash memory? Today, garbage collection is a key technology that has enabled this to work. And today, we're able to write papers that talk about all of these things that made this technology work. Of course, it came at a cost. And I think processing in memory will come at a cost also. And I think we need to solve some of these challenges that I point out over here. With that, I will conclude. I will acknowledge people, funders, and my research group, and I'd be happy to take questions.
Yeah, I think the speaker gave us a huge amount of information.
I guess I've hammered people with raw hammer.
Yeah, actually, I have many questions. So
sure.
The first question is about, just now you talk about the intelligent memory controller. How do you do the intelligent in the memory controller? Just now you see we can select the parts of the memory to refresh. How do you select the part? And what is the overhead for the selection?
So for the specific case of solving row hammer, essentially you need to know which rows are adjacent to the rows that you just activated. And that information needs to be communicated from the memory DRAM chip. Once you know which rows are adjacent, then it's very easy actually, because there's a function, let's say, that gives you that information. But of course, this is just a very limited form of intelligence, right? If you really want to be more intelligent, I believe that requires more information communication from the memory chip And also more information discovery by the memory controller, like which cells need to be refreshed at what frequency, which cells can be accessed with what latency. Actually, latency is also very heterogeneous in a memory chip. You can identify what is the minimum reliable latency at which you can access each cell with. You can store that information. I think that's a form of intelligence. You could consider a primitive form of intelligence, but that's a form of intelligence. And higher level forms of intelligence, I think, is more configurability, more programmability. So you can execute code in the memory controller, for example, that does this for you. You can have perhaps an execution engine that you can program, write software to it. And that software actually does essentially what I suggested, and that can be upgraded in different forms. So if you discover a security vulnerability, for example, you can upgrade that software, just like we upgrade microcode today.
Okay. Done. So any other questions?
Yes,
okay.
please.
Could you give some ideas about how to develop software or algorithms for this
Processing in memory.
memory?
Okay, so that's a very big area for sure. First of all, what is software, right? Software could be compilers, but you're thinking more of the application software. Like operating systems and runtime systems, or? Application software. Okay, I see. So I think then, first of all, you will need to find out, in my opinion, it's good to figure out where are the bottlenecks of your software. Like where do you spend the most of your time? So processing in memory is good for where you have a lot of data movement. If you're doing a lot of computation, for example, there you may not benefit a lot from it. I believe having profiling tools to enable you to understand where your software has bottlenecks, and having profiling tools that can enable you to guess where you should offload things, that will help, for example. And also understanding what type of processing is possible on the memory system will help. I mean, in my opinion, I think we're at the beginning of beginning of our understanding of how to actually develop software for this. We need to develop compilers, we need to develop libraries. I think once you have libraries in place, you can potentially take advantage of those libraries, and you can optimize those libraries, and application software can call those libraries to take advantage of things. But I believe in the end, we need to have an automated framework that can help us identify what parts of the code needs to be offloaded or rewritten to be able to do this. I know there's a lot actually to discuss over here. I cannot do justice to this topic. And there are probably different approaches that we need to follow in research to understand how to do this.
Okay, let's thank the speaker again. We don't have time for more questions. If you have more questions, please talk with the speaker after the talk. Thank you.
Thank you.